So our next speaker in this illustrious list of speakers is Wendy Freedman. So I'm going to just say that when I was in grad school, there were de Vaucouleurs and who was the Hubble constant. It was 100, says de Vaucouleurs. And no, it's 50, says Sandage. And I remember there's some debate at Princeton University where there was no middle ground. Thank you, Wendy. We now have a middle ground for the Hubble constant, which is a huge, huge deal. Wendy was director of the Carnegie Observatories in Pasadena for many, many years and is now at University of Chicago.
Thank you, Katie. Now I'm going to need help getting my presentation. And thank you for the invitation to speak here. I think this is going to be a really fun conference, and it's a real pleasure to be speaking. I didn't know Steve originally early in my career. I knew him through his papers and his books, and later met him and really did get to experience his passion and his joy of doing physics and his kindness. It was really inspiring. I'm going to talk today about some new results from the James Webb Space Telescope in connection with trying to measure the Hubble constant to higher not only precision, but also accuracy. And this is a telescope now that is a 6.5 meter diameter mirror that is optimized for the infrared. So a lot of the systematics that have plagued our measurements of distances in the optical are addressed by having a large telescope in space with high resolution and infrared sensitivity. Okay. So I will not give you today a resolution to the Hubble tension. That probably won't surprise you. But what I will say is that we're making tremendous progress in measuring distances to nearby galaxies. And we're measuring them now at a precision, at least, that is nearing percent level precision, this is not a sentence we could have uttered a decade or two ago. So many different groups now that are measuring distances using different techniques are actually converging on distances, not yet on the Hubble constant, but we're talking about changes that are really small relative to the factor of 2 in the Hubble constant measurements that were there when I began in this field. So we'll hear a lot about Steve, and I'm really, again, very honored to be here today to speak at this conference. Now, that's interesting. We proposed to the James Webb Telescope to measure the Hubble constant using 3 independent techniques. And the reason, of course, is that any method that you use to measure distances is going to have its own systematic uncertainties. That's just a fact. And you will not ascertain the level of those uncertainties, systematic uncertainties, unless you have an external way of checking. And that's been the bane of the existence of the difficulty in measuring the Hubble constant historically is systematics, and systematics. And so we proposed to not only use Cepheids, which is what we used, which Edwin Hubble used, of course, and what we used for the Hubble Key project when Hubble was first launched, but also another method using red giant branch stars at the tip of the red giant branch that I'll describe in more detail, and then a new method that we have just been developing. It's the J region asymptotic giant branch method that uses yet another astrophysical star for which we understand the astrophysics, the underlying astrophysics. So the point is, each of them, again, will have their own systematics, and by comparing those in the end, we can get a robust estimate of the overall systematics. And all of these methods can be used to tie into type 1a supernovae, which allow us to go to greater distances and then into the smooth Hubble flow. Now, JWST has almost 10 times the sensitivity of Hubble at near infrared wavelengths where we're making these measurements, and almost 4 times the resolution in the cameras that we're using in the infrared with the 2 telescopes. And so 3 different methods all applied to type 1a supernova host, and then we can compare the distances in the same galaxies. The galaxies have a single distance. So we're not comparing different regions of the sky using different methods where there could be different systematics that we can't easily disentangle. So that was the point of the proposal with the 3 methods. Now, the challenges in measuring the Hubble constant, again, come down to systematics. And early on, the difference between 50 and 100, a lot of that had to do with the detectors in use at the time, photographic plates, until we got charge-coupled devices and linear detectors. But de Vaucouleurs, as Katie mentioned, was getting values of 100. Sandage and Hammam were getting values of 50. But you can see there were also the measurements in between. It wasn't a bimodal distribution. And people used to joke, so when I was at Carnegie and Alan Sandage was there, they would turn around the corner and the universe would expand or shrink, as the case may be, but it was an interesting time. And the lines here, this is where we are today. So the cosmic microwave background measurements are giving a value of 67, and then the Cepheid-based supernova measurements are giving a value of 73. And it's not simply anymore just the difference between those values that we're talking about, but whether or not the width of the lines now are representative of the overall uncertainties, so that this is a difference that may be telling us that there's missing fundamental physics that we don't yet understand. And the obvious distinction between precision and accuracy, we talk about this being an era of precision cosmology, and I really hope we're going to be talking about an era of accurate cosmology. And this is a tall order, because the microwave background measurements, if the standard lambda CDM model is correct, the value of the Hubble constant that's inferred is better than 1% precision. So getting 1% precision or accuracy with the extragalactic distance scale, that's never been done before. Photometry at that level has never been accomplished. So we have a lot to show that we can reach measurements with 1% accuracy. Now, one of the ways, just as an example of the kinds of systematics that plagued the early measurements of distance, is there were no corrections for interstellar dust. And it wasn't until we got CCDs that we could make measurements at a number of different wavelengths and measure the distances to nearby galaxies, which actually were discrepant at a level of a factor of 2 when I began. And so these are early results that showed that if you could measure the apparent distance modulus to galaxies as a function of wavelength or inverse wavelength, you actually determined a different apparent distance modulus, but with the wavelength information, you could extrapolate based on a fit to the interstellar extinction law and measure the true distance modulus to the galaxy. And now with many wavelengths, and in fact, what we used for Hubble was just V at about 5,500 angstroms and the I band at about 9,000 angstroms that you could correct for reddening. And that was a huge step forward. And these are the results that we got from Hubble. This is the Hubble diagram as plotted originally by Hubble velocity as a function of distance. And Hubble's original measurements fit into this first tick mark here. And we can go a lot farther in distance now. And we used 5 different methods, again, for the reason that we could use the different methods to ascertain what the overall systematics were in these measurements. So the type 1a supernovae go out the farthest. This is just the scatter about the Hubble line. And this is the reason that now today people use type 1a supernovae most often to measure the Hubble constant. So you can measure them farther, the dispersion is small. So we got a value of 72 with a 10% overall accuracy, which was the goal of the project, and resolved the factor of 2 that had really plagued the field for several decades. So if we look at recent measurements of the Hubble constant since the time of the Key project, you can see that the values of the Hubble constant in red here that are based on Cepheid measurements really have remained pretty steady as a function of time. Most of these measurements come from the Shoes group and are giving values between 72 and 74. And you can see also that they're systematically high with respect to the rest of the measurements that are in the literature. These are all other published values. It's a database that was started by John Huckra and then has been updated by Ian Steer. So whether or not this is signaling some sort of systematic effect, we don't yet know, but it's something, again, that partly motivated our proposal for JWST. Now, the measurements of the microwave background and isotropies, I won't spend too much time on this today, but this exquisite fit, again, to the power spectrum for 6 parameters in lambda CDM. And for that model, you infer a value of the Hubble constant of 67.4 plus or minus 0.5, so better than 1% precision. And if you look at the measurements again of the Hubble constant now since the time of the Key project, here again are the Cepheid measurements, and here are now the CMB measurements. And then our group published a value based on this tip of the red giant branch in 2019. We had hoped to resolve the difference between the two, but landed essentially in the middle. And so I think the important takeaway from this comparison is that there are actually two tensions. One is the difference between what you get from the Cepheid calibration compared to the microwave background, and the other is the difference between the tip of the red giant branch and the CMB results. And I just want to note here, before I go on, it's not simply anymore the difference between the TRGB and the Cepheids, because we're now converging, which is new. It's only, we realized this in the last few months. We're converging on the distances, but not yet on the Hubble constant. So it's moved to trying to understand the differences in the supernova calibration, which is interesting. Okay, so this is our group. It's a small group, and these are again the three methods that we have been using. And the route now to higher value of the Hubble constant is overcoming the current challenges. So what are those? One is we have about, in terms of measuring the Hubble constant accurately, there are three current steps. One is the nearby calibration, where we use the distances to galaxies that are based on geometric techniques. And that's a small sample. We've got the Milky Way and stars we can measure individual parallaxes for. There are still systematic uncertainties in the Gaia measurements. Those we hope will be resolved in 2026 with a new release of data from Gaia. We have the Large Magellanic Cloud attached eclipsing binaries. And we have NGC 4258, which is a galaxy that has a supermassive black hole, and we use water masers to infer a geometric distance. Then we have the middle rung, which we can measure, in which we can measure distances using Cepheids or tip of the red giant branch or these JWST stars, and those within galaxies that have had type 1a supernovae in them. So we can then move to rung 3, which is the far flow, where we can measure type 1a supernovae. So if we're going to measure a value of the Hubble constant to 1%, then we need to ensure that the systematic uncertainties in each of these steps is at a level below 1%. And again, that's a tall challenge. So this is what some of the Cepheids look like in the measurement with Hubble in the infrared. So you want infrared observations because dust effects are lower and metallicity effects are theoretically predicted to be lower. But here's the Cepheid, and this is at a galaxy at a distance of only 20 megaparsecs. The sample goes out even to 80, but most of them are less, or around 40 or less. But here's the Cepheid. It's pretty difficult to make measurements at 1% accuracy when the background in which the Cepheid is located is often much brighter than the Cepheid itself. So disentangling the Cepheids, measuring accurate photometry, is a challenge. And there's no way of getting around this because Cepheids are young stars. We find them in the disks of galaxies, and that's where star formation is occurring, where there's lots of dust, and you just can't get around it. That's what it looks like in the near infrared with JWST. So our ability now to make more accurate measurements has improved considerably with JWST. Here's another example. Again, there's the Cepheid. So the Cepheids are found in the optical. That's where the amplitudes of these stars are largest. And then they're followed up in the infrared. And again, here's what happens when we go to JWST. So at 20 megaparsecs, the stars are crowded again by these stars. So the area we're looking at is 8 times larger than comparable for the fixed resolution of your detector at the calibrating galaxy, NGC 4258, which is at 7 megaparsecs. When you go to 40 megaparsecs, you've got 33 times the area within that same fixed resolution element. And 60% of the SHOES sample lie at distances greater than 20 megaparsecs and 25% beyond 40. So again, we're trying to get 1% accuracy. then JWST is going to be a way of distinguishing whether or not crowding of these stars is critical. So here we are again with Hubble over here. You can see for different galaxies here, the effective crowding, and this is the 1.2 micron filter with JWST, and these are the optical bands from Hubble. The crowding's not nearly as bad in the optical. And you need the optical still to correct for the effects of dust, as I showed earlier. Okay, I'm going to concentrate most of my remarks today on the tip of the red giant branch because it's the method that we have the most data for, both from Hubble and from JWST. Just going to check time here because I don't want Katie's water gun. Good. I just want to monitor where I am. Okay. We blinded ourselves in doing the analysis, which is the first time in this particular kind of measurement that we've done that. And all of the analysis was carried out with an arbitrary 0 point, no knowledge of the distances, no knowledge of the Hubble constant during that analysis. So we did the photometry, all of the photometry quality cuts, we fit the period luminosity relations for the Cepheids. We did these so-called artificial star tests where you inject stars of known magnitudes similar to the Cepheids and then extract them in the same way as we do for the real data. We measured the luminosity functions for the tip of the red giant branch and JGB and so on. So all of that was carried out before unblinding. And this JGB analysis was carried out completely before unblinding. So I'll just state that in terms of the tip of the red giant branch, there was some subsequent analysis in terms of the spatial cuts, and the Cepheids, we found an error in the pipeline, and that was corrected. It was just an additive correction, but just formally, it wasn't completely blinded. But 98% of the analysis was carried out blinded. These are the galaxies in our program, and the red lines indicate the positions of the NIRCam JWST field locations. And so we had centered these on the Cepheids and the disk. The JGB stars are in the outer disk, and the tip of the red giant branch, we can make a measurement in the halo of these galaxies, which is a big advantage because there's essentially no dust, there's no crowding, and we understand the physics of these stars very well. So the three methods here, and just showing you in an HR diagram, this is luminosity as a function of temperature going this way. This is the observational version of the Hertzsprung-Russell diagram. And the Cepheids are the brightest of these stars that we're looking at. And here's the position of the JGB stars. And this is the tip of the red giant branch. So these stars are located in different environments. They have different chemistry. They have different crowding, different amounts of dust, and they're at different evolutionary stages. But the advantage now is we're using the same cameras, the same calibration, the same detectors, point spread functions, and so on. So in terms of comparing the relative distances, then this is the first time we've been able to do that. Now, the three methods have different levels of complexity. The period luminosity, we refer to a period luminosity relation for Cepheids, but it's actually a period luminosity color metallicity relation. There's the luminosity or the absolute magnitude is a function of the period of the star, the color of the star, a term due to the abundance or metallicity of the star, and then, of course, an absolute calibration bringing in the 0 point. The tip of the red giant branch method, if you confine yourself to optical wavelengths around 9,000 angstroms, where we originally did the Hubble measurements, the absolute magnitude is a constant. There are no other terms. It's much simpler. If you go to the J band, which is what we're doing now with JWST, you have a slope to the relation, but again, it's just one term. And then for the JGB stars, the luminosity is constant. So there is a level of complexity still with the Cepheids that make them more of a challenge. Now, the tip of the red giant branch, as I mentioned, has well understood physics. These are stars that have a partially degenerate helium core. These are low mass stars comparable to the mass of the sun. And the stars are climbing the red giant branch. They're burning hydrogen in a shell that is dumping more helium onto the core. and the temperature is increasing. These are degenerate stars, so they can't expand and cool. And when the temperature reaches about 100 million degrees, then the triple alpha process can ignite, and you get a runaway, thermonuclear runaway. And the star settles onto what's known as the horizontal branch at a lower luminosity. But the observational, empirical then fact is that we can look at these stars and we don't see, after the tip of the red giant branch, these stars don't ascend past a given luminosity. And because of the degeneracy and the helium ignition occurring at an almost constant core mass, there's a predictable luminosity, and it's well understood. People have modeled this now for decades. And here's the observational color magnitude diagram. And you can see, again, the tip here. There are asymptotic giant branch stars here, but we measure the luminosity function, and then we've used image processing techniques, edge detection software. We've done many different ways of measuring the tip, do artificial stars, et cetera, to determine how well we can measure this feature. It's very simple. Maximum likelihood techniques, Nobel kernels. So here's some of our JWST results for the tip of the red giant branch. Here at 7 megaparsecs, here at 15 megaparsecs and 22. We've tried to ensure that we have high signal to noise, but the measurement of the tip now in 10 galaxies with JWST is well determined. Now I'm going to speed up here a little. I just want to make the point that the distances now have converged. Our original measurements in 2019 of the tip of the red giant branch and comparison with the Shoes Cepheid distances, they're now agreeing at the 1% levels. I'll show you in a moment. In 2019, there was a 3%, so 0.06 magnitudes, equivalent to a 3% difference in the distances that we're measuring with the Cepheids and the tip of the red giant branch. That now the Shoes measurements have converged to the tip of the red giant branch distances. So if we compare the HST and the JWST measurements from our own group, they're agreeing at the 1% level. The HST measurements are turning out to really hold up. And on the right, I'm showing the comparison with the Shoes 2022 data. They're agreeing at the 1% level. And of the galaxies that overlap in the 2016 measurement from Shoes, there was a 4% offset. And that now has converged to the TRGB distance scale. I'm looking here at the absolute magnitudes of the supernovae in the calibrating sample, and you can see that there are large offsets between 2022 and 2016. Some of the differences were as large as 15% in distance, which is large when you're talking about trying to make a measurement at 1% overall for the Hubble constant. And here's a comparison when we join the samples of our HST and JWST measurements for the tip of the red giant branch compared to the Shoes measurements, and you can see how well the distances have converged. So this is really new in the distance scale. And these are very different groups, very different kinds of analyses that are now converging. That's, and this is just a quote from Shoes at how well the distances have converged. But note that they've converged to the tip of the red giant branch distance scale. And I just want to point out, there's been some talk about whether our measurements are representative of the samples large enough. This is the Shoes distribution of their 42 supernovae, or the 37 galaxies that have type 1a measurements nearby. And this is the tip of the red giant branch, so it's fairly consistent. And this is just a comparison of our own measurements relative to the distant sample of 300 supernovae. Again, they're not too dissimilar. I'm just, again, in the interest of time, I'm going to speed up a little, but I just want to point out that where we're now seeing these differences is the comparison of distances for the local supernova sample. And so it's just interesting that the galaxies with the smallest errors are giving different values for the absolute magnitude of the supernovae, which is what sets the value of the Hubble constant. I'm, again, in the interest of time, I won't say much about the JGB method, except that it's completely independent, different kind of astrophysical object. We can measure its luminosity. with high accuracy. These stars in the infrared have a very constant luminosity, and we've carried this out into JWST, and the results are looking very promising. Still a small sample, but that will be increased in future, and that's the comparison again. We all know about Cepheus. They've been a historical standard for a century after Hubble. And we've extended that to JWST. I just want to say a few words about our supernova, distant supernova sample. And this is a project that we carried out at Carnegie using 3 different telescopes, depending on the luminosity of the supernovae, so that we could follow them well. This is something Mark Phillips and I carried out at Las Campanas in Chile. It is a data set where we aimed to really get high cadence observations of the supernovae at multiple wavelengths so that we could look for environmental effects, correct for reddening, and so on. And also obtain spectra to get accurate K corrections. And this is the sample that we're using to measure the Hubble constant and tie into the distant Hubble flow. So a lot of the other surveys don't have this kind of coverage. And we paid a lot of attention to the systematics, and we tested the detectors on an annual basis in terms of measuring the flux, make sure there were no changes, a function of time, and so on. So here's the supernova Hubble diagram based on the supernovae for our sample. And these are the results from tip of the red giant branch, combining our HST and JWST results. And so we have 8 parameters that we're looking at. This is the magnitude of the supernovae. We allow for the color of the supernova and also the mass of the progenitor. Here's the reddening correction, and done different analyses with different packages for Markov chain Monte Carlo. And so we are getting a value of 70 kilometers per second per megaparsec, including an uncertainty here of about 3% at the current time. That will improve soon, but I think it's a realistic estimate of where we are now. Great, thank you. Okay, so what do we need to do to improve how do we get at this tension? And I think the obvious next step is that we have to increase the numbers of supernova host galaxies with accurate distances. And this is difficult because supernovae are rare. They happen about once per century in a galaxy. And so the numbers of nearby galaxies where we can actually measure Cepheus or tip of the red giant branch or other methods is small. It's about, we can find these every 1 to 2 years, where Hubble can then go on and we can make these measurements. So increasing this sample is not going to happen quickly, but there are now surveys that are trying to increase the range. And I think with Roman and tip of the red giant branch and JGB, we're going to be able to increase the volume and significantly increase this data set. And the problem is that now we're looking at differences having to do with the weighting of the supernovae in this small sample. And so we're talking about 1% and you know, is this a 3 or 5 or 2 sigma tension? It all comes down to the uncertainties. And that, I think, is not a good place for cosmology to be. And we need to really improve that. We still need to show that galaxies with distances in excess of 30 megaparsecs have no systematic errors due to crowding. And I think, you know, the argument has been made that with 8 sigma confidence, there is no issue with crowding. But if we look again, this is comparing the 2016 and the 2022 photometry for the distances to these nearby galaxies. Here, and you can see these large 15% excursions, and 2 of the galaxies essentially lie, you know, there were no differences. These are easier galaxies to analyze, are 2 of the 5 that are now being used to say that there is no effect due to crowding. And again, some of these more distant ones have yet to be tested. So I think, you know, there's room here that we need to absolutely ascertain that this is not an issue for the more distant galaxies. And the images that I showed you are for the relatively nearby galaxies. It's only increases in the challenge as you go to larger and larger distances. So this is just a summary. These are the PDFs of measurements of the Hubble constant. This is what comes from the Planck measurements. Here's the recent DESI measurement, and here's where we are with the Chicago Carnegie Hubble program. And let me just make a few concluding remarks and I'd say that JWST is really ushering in a new era and in terms of the accuracy with which we can make measurements of the Hubble constant. And it's similar to what it was like when we launched Hubble and could get above the ground and got higher resolution. So we are learning a huge amount. As we can see, the distances now are converging and all of the distances are now agreeing at a level that we haven't seen before. But the differences in H0 have not disappeared. They're coming now from the nearby supernova sample. And that, I think, again, it's reassuring because this is an empirical issue that I think we can solve relatively quickly. So we need to increase the sample size, particularly for the Cepheids and for the JGB method now to bring down the statistical uncertainties and to allow us eventually to get to H0 at the 1% level. We still need to ensure that the distant galaxies are not suffering systematically from crowding effects. And I'll just leave you with the result. At the moment, we are measuring a value of 70. It's consistent for all three methods. And I will add a conservative uncertainty at this point of 3%. And I'll stop here. Thank you. Okay.
Hey, Wendy, we're starting off pretty well here, I'd say. We started off with particle theory. Now we're in, thank you. Particle theory. Now we're in astrophysics, and let's take some questions. Netta.
You want the microphone?
Oh, wait a minute.
So you say the distances all agree for those that you have the data, and the difference in the Hubble constant is just from the nearby supernova galaxies. Can you check the distances with the red giant branch for those to see if the
These
distance
are the distances from. So recall that there's the nearby calibrating sample where you can measure both Cepheid, TRGB, JGB direct distances, and they have supernovae in them. And those are used to step out into the Hubble flow and calibrate those. So the type 1a supernovae, you only get a relative distance. You have to have galaxies for which you can determine absolute distances that are near enough to tie in then to the geometric calibrators locally. So it's this middle rung that I showed you where this is turning up. And the surprise to me is that, you know, as I look at this sample, if you do a jackknife test or you compare the uncertainties for the supernovae, the tip of the red giant branch compared to the Cepheids, they have very different uncertainties and very different weights. So you can move the Hubble constant by more than the quoted uncertainty or comparable to the quoted uncertainties, which is indicating that the uncertainties are larger, I think, than have been taken into account. And if you look at the change from the early observations, the distances have changed by a significant amount. The weighting of the supernovae has changed by a significant amount. The slope of the metallicity relation has changed. The slope of the period luminosity relation has changed. The period cutoffs have changed. And each of those leads to shifts that are systematic. So, and it's just still a small sample. This is it's statistically a small sample. So we have to increase the sample.
Maybe I can just make a fun comment. Rich God some many years ago did the statistical analysis of the slide you showed of the different Hubble determinations in the early days. And the mean, which like to do statistics, as you know, and the mean that he got for that was 70 plus minus something. We are reaching now to a point where we are getting, again, 70, and the Hubble tension is, again, between 73, 74, and 67, and you get the mean again. If Rich did at this, the mean again, you'll get it at 70. So it's really a curious and interesting
Yeah,
situation.
the other interesting thing is there's been a lot of effort to try and explain the Hubble constant of 73 theoretically. And that has turned out to be really difficult to do. And what's surprising to me is how hard it is to break lambda CDM. I mean, you might get to 70, but it's hard. But getting to 73 or 74 turns out to be very difficult. Now, and it may be that's what turns out to be the case, but I think that we're not there yet. Certainly not at 5 sigma in my view.
I just wanted to comment, it is mind-boggling to me that we're not at 50 versus 100 anymore, and a lot of that is thanks to you, Wendy. This is phenomenal. You can't make a projection about time, Roman, how quickly we might get there, can you?
I think, even with a couple more years of JWST data, I think a lot of this is going to become clearer. I think, Roman is due to be launched in a couple years, say. My own view is that we're unlikely as a community to be completely confident until we have a different, completely independent way of doing this. I don't know whether it's gravitational wave sirens or something that it doesn't depend on luminosities and distances. But I think we're nearing the point where we can say with confidence whether or not there is a significant fundamental physics that's missing from the standard model. I think that's going to be within the next few years.
Wow, fabulous. Well, thank you so much, Wendy.